Nix lets you build any version of any software on any machine. This is a big claim to make, and there are certainly caveats to this statement that prevent it from being 100% true, but it is much closer to the truth than you may think. I wanted to understand how Nix achieves this, but most resources I found were about how to install and use Nix and did not really explain how it worked. I want to try and create that resource that I wish I had when I was learning Nix, and give an answer to the question, what is Nix? The answer to this question can take at least 3 different shapes, and that is confusing. It all only really started to make sense for me when I started to understand Nix from the bottom up. So let's start with how Nix came to be. Nix was built as part of the PhD thesis by Elko Dolstra. It is titled Het pure functionele software deployment model, which means the purely functional software deployment model. The thesis is about how to deploy software reliably. Deployment in this context means, how do I get a piece of software running on a given machine? One solution to this deployment problem is distributing binaries. You have your source code, and maybe you can't or won't give other people access to it. So instead you compile your code and distribute the resulting binary. This is very common, for example when you download Firefox or any closed source application. However, a lot can go wrong in this model if it's not done with meticulous attention to detail. For example, the user might have a different processor type or a different operating system, and that means the binary won't work. We also live in a world where dynamic linking is the default, so binaries often rely on dynamic libraries to be present to be able to run it all. If one of those dynamic libraries is missing or has the wrong version on the user's machine, the binary won't run. This is what makes copy the binary as a deployment solution extremely fragile. With open source software, the source code can be easily accessed and shared. In fact, most open source software comes with some sort of build recipe. On the low-level end of the spectrum, you'll find bash scripts or makefiles to codify how a project is built. Most modern languages come with tools out of the box that automatically build a project for you. In this deployment model, the source code gets distributed to the user's machine and is compiled there. This means that the build recipe can tailor the process to the exact system the software is supposed to be running on. This makes this solution generally much more robust. For Nix's goals, however, it is still not robust enough. For example, the user's machine might have a different version of the language's toolchain, causing incompatibilities. And problems surrounding dynamic libraries are also still a thing. Apart from that, the approach of compiling software for every deployment is slow and wasteful. Deploying to 10 machines means building it 10 times even if the machines are virtually identical. The underlying problem here is that all of these solutions to deploy software don't fully capture everything that can affect the buildability and the runnability of software. To tackle this problem, Elko developed a domain-specific language, or DSL for short, and called it Nix. Both the language's design as well as its runtime are designed to codify build instructions and ensure that a build can be reproduced reliably. Basically, as long as you have the same processor type and the same operating system, Nix's goal is to output the exact same build artifact down to the single byte. Because Nix's origins are in academia, it is not just a DSL like makefiles, but it is of course a Turing-complete, pure and functional programming language, taking lots of inspiration from Haskell. Don't let this scare you though. To play around with Nix and the Nix language, go to nixos.org and follow the instructions. The installation process can seem a bit scary as it creates new users and groups on your system. It feels even scarier on macOS, where it also creates a new partition on your disk. There are good reasons for these things, but for now, it's fine. Just trust me. With Nix installed, we can get going. I want to give you a speedrun of the Nix language so that you can read the code samples in this video and also other people's Nix code. This will be fairly rapid fire, so feel free to pause and use Nix REPL to try things out as we go along. Line comments start with a hash symbol like in Ruby or Bash. Nix also has block comments with a familiar C syntax. This is a number and this is a floating point number. Strings use double quotes. Double single quotes are also strings, but those can span multiple lines. You can inject values into strings using a $sign with curly braces. This is an array in JSON notation. In Nix it is called a list and it looks like this. Note the lack of commas. Here is an object in JSON notation. And in Nix it looks like this and is called an attribute set. Yes, those are equal signs. And yes, those are semicolons. They must come after every single attribute. This is a long-form JavaScript function. As you may know, there is a shorter arrow function notation in JavaScript, and if you skip the curly braces, the return is implicit. In this form, JS functions and Nix functions only differ in that Nix functions use a colon instead of a fat arrow. Let's say this function is called f. Then you would invoke it like this, without parentheses. This takes some getting used to, especially for nested function calls. In most languages, functions can have multiple parameters. In true functional programming fashion, however, functions in Nix can only take a single parameter. For multiple parameters, you would nest functions. There are some upsides to this, like partial application, but you actually won't see functions written like this very often, because instead you can use an attribute set as the single parameter for a function. To invoke this function f, you'd pass in the attribute set. Nix will validate whether every expected parameter has been provided. If, say, c is missing, Nix will throw an error. Parameters can also be made optional by providing a default value using the question mark operator. Like in many other functional programming languages, everything in Nix is an expression. So for example, if-else is an expression whose value is the result of the branch that was taken. On that note, while the REPL does let you assign and reassign values to variables, mutable variables are not a thing in pure Nix code. You can only bind values to identifiers, but you cannot change them afterwards. So while I was pretending to name a function f using a comment, the correct way in Nix is to use a let-in expression, like this. Bindings are effective immediately. And because Nix is lazily evaluated, you can use one binding in the definition of another binding within the same let-in expression. Now a last piece of Nix syntax. Nix has the with expression, which brings all attributes from an attribute set into the scope. So if I have an attribute set and want to access many attributes from it, I could use with to simplify this expression. However, this syntax is discouraged and you should not be using it. I'm only including it because it still appears in a lot of Nix code. What you should be using instead is the inherit keyword that works in attribute sets and in let-in expressions. This way you explicitly list which attributes to bring into the scope, which allows LSPs and other tools to do better static analysis. And now you can read Nix. And that's important because, quite honestly, the documentation situation in Nix is not great. So having the ability to dive into other people's Nix code is essential. Nix comes with a minimal but powerful collection of built-in functions, most of which are on the global called builtins. For example, attribute names gives you a list of all attributes that are present on an attribute set. Similarly, function args gives you a list of all arguments that a function accepts and tells you which arguments have a default value. Of course, Nix allows you to break up your code across multiple files. Here is a file that just contains the number 4, and in a second file I can import that file using a relative path. This import expression will return the value of the Nix expression that's inside that file, so in this case 4. There are more built-ins, but nothing that is worth spending time on right now. It is much more important that we talk about the two language features that make Nix a domain-specific language specifically for building software. The first thing is file paths. In most languages, paths are just strings in quotes. In Nix, they're first-class citizens with their own syntax. If you drop the quotes, you have a Nix path. The value of this path is shown in the REPL as the absolute path to the file or folder it is referencing. However, the REPL is kind of lying to you because that is just the display value of the path. The actual value becomes visible when you turn the path into a string, using string interpolation or toString. What you see here is a path to an item in the Nix store, and the Nix store, along with its naming convention, are a core part of Nix's solution to the software deployment problem. Theoretically, the store could be put anywhere, but you should really never change it from its default place, which is /nix/store. The store path also contains a hash, which depends on the file contents of the referenced file. That means two files with different content get a different store path. I'm hand-waving a bunch of details here as the hash also includes other data points like the file name. So just because two files have the same content does not necessarily mean that they have the same store path. The details of this procedure are quite long-winded and not necessary to understand in detail. But if you're curious, open the PhD thesis and read the chapter titled The Extensional Model. What is important to know is this. Every time a path is evaluated in one of your Nix expressions, whether it's a single file or a whole folder hierarchy, it is copied to the Nix store, made read-only, and given a unique hashed file name. In a way, the Nix store is a content-addressable, immutable data store, somewhat similar to how Git works. This design of the Nix store is what makes Nix so powerful when combined with the other distinguishing language feature, derivations. Derivation is really just another built-in function that executes a command and captures the produced output. For example, let's say we wanted to compile a C file. The derivation function takes a couple of parameters that we need to provide. First, the derivation needs a name, as each item in the Nix store has a name. Then the derivation needs to declare what system it is targeting, as different targets may require different build instructions. Here we want to use Clang to compile C code, and we want to compile our main.c file. Note that this is a Nix path, so we know that this file will be hashed and copied to the Nix store. The derivation function really only cares about the attributes called name, system, builder, and args. The value of any additional attributes will be made available via an environment variable. Clang sadly has no way to specify input files via environment variables, so to be able to tell Clang what files to compile and keep things explicit, I'm going to use some awkward inline bash scripting here. Instead of using Clang as the builder directly, I'll use bash, and then we can invoke it with a bash script provided as a multi-line string. Now inside the script we can invoke Clang, and because it's bash, we have access to all environment variables in the familiar notation. This is how we get access to our source file. The next step is to use Nix instantiate to store the build recipe itself in the Nix store. This does not execute the build steps, but is about serializing the derivation in a deterministic way. The serialization format is fairly simple, but not pleasant to read in its raw form. Running Nix derivation show pretty prints the serialized derivation as JSON, which is a lot nicer to look at. And here we can easily see how every attribute we passed to the derivation function was turned into an environment variable. In fact, we can see how the relative file path for our main.c file was turned into an absolute path in the Nix store. Executing a derivation's build instructions is called realizing a derivation, and can be done with Nix store realize. So let's do that. When a derivation is executed, it is done so in a sandbox. The sandbox is an empty, temporary folder with all environment variables unset. This prevents the builder or other tools from accidentally pulling in system configuration files or system libraries, which would make the build non-reproducible. This build failed because Nix couldn't find any output files being created. Apart from the temporary folder to build in, a derivation is also given another temporary folder called out, where all outputs should be placed. If that path remains non-existent, it's an error. So all we need to do is to tell Clang to put the output into that location. To try again, we have to serialize and realize the derivation again. We could do each of these steps separately as we did before, but luckily there's Nix build, which does both in one go. It also creates a convenient result symlink in our current directory, linking to the item in the Nix store that contains the derivation's output. Some of you may have been pulling their hair out because I did a big bad thing. I used a hard-coded absolute path for both bash and Clang. This means I am relying on the system's C compiler, and this is very much not reproducible, as a different system might have a different default C compiler and could produce different or broken output. So what is the right way to do it? Nix solves this problem by using Nix. As Nix is about building software, we could just build a C compiler. This way we know that we will be using the exact same version of the same C compiler every time. Let's say we have decided to go with Clang 16. We can grab the source code for Clang 16 in a tarball from GitHub. In fact, Nix has a built-in function for downloading tarballs from URLs. You could skip the SHA-256 attribute, but then Nix would have to download the file first to be able to know if it has changed. If you know the tarball is not going to change, providing the hash allows Nix to skip re-downloading. It also protects against supply chain attacks. The easiest way to figure out the hash that Nix is expecting is to set the hash to an empty string. If you now try to build this derivation, Nix will complain and tell you the correct hash. Now that we have the hash, we can use the system's tools to unpack and build Clang. Let's store this derivation in clang.nix and build it. Nix build will download the source code, verify the hash, and build it using the tools that are available on the system. The output is a well-defined version of the Clang compiler that is now accessible as a Nix store item, and we can use this Clang as a build tool going forward. However, because we used system tools to build it, it also relies on system libraries like libc or libc++. That means that while this compiler will generate the same binary code for a given C code, it might not compile on other systems. As long as a Nix store items requires items from outside the Nix store, it is considered impure. To get out of this pickle, we do the same trick again. we use our well-defined compiler to build our own libraries. Let's say we want to use glibc version 240. And just like before, we download the tarball from GitHub. To use our own clang, we import it and pass it in as another attribute to the derivation. Then in the build script, we set the ccn variable to our own clang, which will hopefully get picked up by autotools, makefiles, and those sorts of things. What we see here is the ability to nest derivations. If we look at the serialization, we can see that the derivation passed to another derivation is resolved to its output path. That means that the nested derivation is built first and its output is handed to the derivation one level up. Now, because the Nixstore path for clang appears in the glibc derivation, the hash for glibc itself is dependent on clang. If clang changes, so does its hash, and as a result, so does glibc's hash. This is a Merkle tree, and you may be familiar with this concept from Git and other tools. Nix uses the Merkle tree to ensure that software is always built with the exact same dependencies and build tools. It also uses it to determine whether a derivation has been built before. That's the power of having a hash in the file name of all Nix store items. An interesting implication is that we could compile the same glibc multiple times with different configurations. For example, maybe we need a version of glibc with SIMD support for one project and a version where SIMD is firmly disabled. Both derivations would be identical except for this one flag, but that's enough to change the derivation's hash. And that means they would end up in different places in the Nix store. Both variants can coexist without overwriting or interfering with each other. And other packages would be able to specify exactly which version they need. This is a huge improvement to how most POSIX systems currently work, where we install all libraries to user lib and just hope for the best. Let's go back to our impure clang. It's impure because it relies on system libraries. So let's call this one clang stage 1. We can now update our clang derivation to instead use our pure Nixified glibc library and other dependencies. If we now rebuild clang, the resulting output will only rely on well-defined pure libraries in our Nix store, and this is called the stage 2 compiler. This clang is the same version as our stage 1 compiler, but is itself also pure. That means it relies on nothing outside the Nix store and is completely independent from the host system's tools and libraries. We can keep playing this game with all the tools that we rely on. We can now build a pure bash, tar, make, cmake, git, and so on and so forth. This collection of pure build tools is called the standard environment. And as is such a fundamental requirement to use Nix, Nix provides it out of the box for you. But Nix actually plays this game to its logical conclusion, and that's what Nixpkgs is. Nixpkgs is a huge collection of Nix derivations for almost any software package. It is arguably the most common meaning of what people are referring to when they say Nix. At the time of recording, Nix is both the biggest and the most up-to-date package collection. This graph compares package managers and their repositories. On the graph, the number of available packages is on the x-axis. The y-axis shows the freshness of the packages. A package is considered fresh if the version available is the most recent publicly available version. So with Ubuntu being here and Nixpkgs being here, it means Nixpkgs has about 3 times as many packages as Ubuntu, and most of them are fresh. That's quite an achievement. As I already hinted, Nix is able to detect whether a package needs to be rebuilt or not. But even just building this entire bootstrapping toolchain once, which technically also contains a stage 3 clang, would take a really long time. That's why Elko also designed a way for different Nix installations to share binary artifacts via remote binary caches, even across the internet. As each Nix derivation is built in a sandbox where nothing is available by default, every dependency must be explicitly passed into a derivation. That means that Nix can analyze every derivation's dependency tree. With this command, you can show a derivation's direct dependencies. With this command, you can show the transitive closure, meaning all direct dependencies, the dependencies, and so on and so forth. This understanding, combined with the fact that all pure derivations can only rely on results from other derivations, is what allows Nix to be fully self-contained. Caches.nixos.org is such a remote cache for all of Nixpkgs. That means that most of the time installing a package from Nixpkgs is nothing more than downloading a couple tarballs and putting them into your Nix store. Of course, security is an important factor to consider here, and the solution must prevent attacks like cache poisoning. The thesis covers all of this, but explaining it would blow the scope of this video. If you are curious though, I will yet again refer you to a chapter in the thesis called the intentional model. Now back to our C program. Let's stop bootstrapping build tools and use the build tools provided by Nixpkgs. To get access to Nixpkgs, we need to download and import it. Just like before, we can download a tarball from GitHub. There are shorter ways, but they're somewhat discouraged or impure, so I'll stick to this for simplicity and consistency. I will hide this function preload as it's quite wide and just distracting. Just remember that from now on, packages is our handle on Nixpkgs and all its 90,000 packages. To make this derivation pure, we could replace each reference to a tool with their Nixpkgs counterpart, like this. However, this will get messy very quickly. Instead, we should use the standard environment that Nix provides via the stdenv attribute in Nixpkgs. From there, we can call the mk-derivation function, which is a high-level wrapper around the basic derivation function. mk-derivation is built for the standard workflow of downloading a source code tarball of C or C++ code, unpacking it and building it using autotools. To this end, mk-derivation populates the sandbox by default with useful tools like clang, make, autotools, tar, and so on. This allows us to remove a lot of the attributes as they are set to the correct value by default. Native build inputs are tools or libraries that are needed for building. We could specify clang here, but as I said, it's provided by default. There's also build inputs, which are dependencies that are needed at runtime, so dynamic libraries or configuration files, for example. As our program is not a tarball from the internet, we do not need to do downloading or unpacking, so we need to tell mk-derivation to skip that step. For the build phase, we provide a bash script to describe how building works, and in the install phase, we populate the output folder. This shows another Nix convention that is important to follow. Every Nix derivation should create an output folder structure that matches the file system hierarchy standard, or FHS for short. This just means that the output folder should have the familiar folders like bin for binaries, lib for libraries, and include for headers. So much for C. Of course, you could bootstrap support from this for any other language. But luckily, Nixpkgs provides support for numerous other languages and frameworks. For example, there is build Rust package, which builds a Rust project for you. It looks at your cargo log file to download all the sources of your transitive dependencies, validates their hashes, and puts them in the Nix store. This way, you will be able to rebuild your project even if you're offline, if crates.io ceases to exist, or someone just unpublished a version of a library you are using. There are similar helpers for Node.js projects, for Go projects, for Dart projects, for .NET projects, for Ruby projects, and so much more. Lastly, there is lib, which contains utilities. There you will find even more ways to download source code from the internet, but also functions to work with Nix values, like checking if a string starts with a prefix, map a function over a list, or deep merge attribute sets. The built-ins, the lib, the stdenv, and all language and framework helpers are documented in the manual, which I can highly recommend to bookmark. There's also noogle.dev, which lets you search for Nix functions by name. For completeness sake, I should mention NixOS. NixOS is a Linux distribution that not only puts Nix at its center for package management, but for the entire system's configuration. In this world, everything is configured through Nix expressions rather than program-specific config files and stored in the Nix store. This has many interesting implications that I won't go into, but that's the third and final meaning of what people could be talking about when they mention Nix. And yet none of them are really the same. So this is how Nix works. There's way more to talk about. For example, there's flakes as the new experimental way to write derivations. They make it a lot easier to pull in additional source code or Nix helper libraries from GitHub and other online sources. Cacheix allows you to set up binary caches for your own Nix projects. Or Home Manager in Nix way to manage your dot files. I will link to all of these in the description and add some other additional resources that I found useful throughout my learning journey. For me, Nix has mostly replaced Docker on my servers and Homebrew on my workstations, and I don't think I'll go back.